principal assumption was different scaling parameters were all integer powers, positive or negative, of one parameter. And in my talk, I will speak about the situation where this is no longer the case. So we have incommensurable contraction. And so this is our contraction operator. I put this multiply in front of this for the sake of unitary operator. And I consider the commutative D-star algebra generated by this operator. So closure of this sums in the operator in L2 or Rn. And the Gelfand-Naimark theorem, the simplest case, tells us that this algebra is isometrically isomorphic to the algebra of continuous functions on the circle. So the general version says that this is isometrically isomorphic to the algebra of continuous functions on the maximal ideal space, but in this simplest case, the Gelfand transform acts as a homeomorphism of this maximal ideal space onto the spectrum of the operator P, which is the entire set. This is quite simple. Okay. But let us now take two contraction parameters with incommensurable logarithms, consider these two operators together. So we built the corresponding algebra as a closure of the finite sums of this. The representation of an operator in this form is unique, of course, but which is the first step in studying this algebra. This is this lemma. It's where the story begins. So I can simply put it like this, that incommensurability means this estimate. This is the principal lemma. It's not hard to prove at all, but it looks very natural. So we estimate the norm, the operator norm, from below, like square root of the sum of squares of modulus of this coefficient. It's because these parameters are incommensurable. And this lemma helps us prove, study the structure of the maximal ideal space. And it's quite natural to, it's a natural conjecture that this maximal ideal space is now not circle, but two-dimensional torus, a two-dimensional torus. First step is very standard. This we introduce this mapping. It helps us to obtain that the maximal ideal space is homomorphic to a compact subset of the torus. But the question is, does this K coincide with the entire torus? And the question is yes. So this is the theorem. I can give you the sketch of the proof. First of all, we have this isometric isomorphism such that this operator is maps to this trigonometric polynomial, and our key lemma assures this estimate, which means that the uniform convergence to zero of any sequence of trigonometric polynomials of two variables on the set K implies the mean square convergence of the sequence to zero on the entire torus. And it only remains to ensure that this is only the case. This can be only where K coincides with the whole torus. to this end, we assume the contrary. The set the set is non-empty, and since it is an open set, there exists a function, a smooth function f, not identically 0, and such that its restriction to k is 0. Partial sums of the Fourier series for this function being trigonometric polynomials converge to f in L2, but they approximate f uniformly on the torus as well. They therefore converge uniformly to 0 in k. This contradiction with the k estimate proved this term. And now this correspondence is uniquely extended to an isometric isomorphism of the algebra onto the algebra of all continuous functions of the torus. And now an example. Let us calculate the norm of any of such operator. The theorem tells us that it equals the maximum of this model. And if suppose the operator looks like this, it's 3 terms here. And the only thing we have to do is to consider this very simple function of lambda and w, which is 1 plus alpha lambda plus beta w, and of course the maximum of its modulus equals this. And if we want to know when this operator is, its Hermitian part of this operator is positively definite, then we come to this very simple network. It's positive definite. So incommensurable contractions, function of 2 independent variables. At the same time, if we put here p square, for example, p square, instead of q, this p square might be arbitrarily close to. But this is p square. Then the norm of this operator is equal to the maximum of the square root of the expression. You don't need to look carefully. The idea is very simple. Here we have 1 plus alpha lambda plus beta lambda square. That's all. The difference. Two independent variables on the torus and one independent variable on the circle. It's lambda square. Very simple. But we come to absolutely different result, conclusion. And this, the norm of this operator is less than before. Equality is only possible for special arguments of these complex numbers. And the positive definiteness of its Hermitian part is expressed by the less restrictive condition. Here it is, rather than this. And we conclude that the norm and the spectrum of the operator change abruptly in the neighborhood of the value q equals p squared, which means that algebraic properties of operators with contracted arguments are unstable with respect to small perturbations of scaling parameters. Okay. The algebra APQ is not enough, and we consider also operators by multiplication by homogeneous function, continuous in Rn minus 0, and of course the algebra of such operators is isometrically isomorphic to the space of all continuous functions on the sphere, if we consider them separately. And it's obvious that they commute with the operators from these operators commute with operators of contraction. And now we consider the algebra generated by all of these operators. And here, this lemma plays the analogous role, similar role. It gives us the estimate from below for the norm of any of this sum, any of such sum. The proof is a bit more complex, but it's completely analogous to the previous case. And we pass to the commutative B-star algebra obtained by the closure of the set of these finite sums, and obtain the analogous result. So the space delta PQG of the maximal ideals of this algebra is homeomorphic to the direct product. So here we exploit the same idea. We come from the maximal ideal spaces of these algebras alone to the product of these maximal ideal spaces. And then our algebra is isometric isomorphic to the algebra of all continuous functions on this direct product of the torus and the sphere. And this is the evident corollary from this result. How do we know when our operator or its Hermitian part is positive? So now we pass to the Dirichlet problem for our functional differential equation. There are not very many equations here, so I don't numerate them. And this, when I say the if d here, I mean this. And the if d is called strongly elliptic in omega if the Gordon type inequality holds. And I just want to say that if omega contains the origin and the coefficients are constant, we immediately can replace this equation by this inequality by the following one. And what is the advantage? Not only that we omit this lower term, it's not very important. Of course, we have this, it's quite evident. But what is more, we allow to function W to have an arbitrary support. The support is not restricted by the domain. It may have an arbitrary support from Rn. So we come to the inequality in Rn. And of course, this it is obvious that this helps us to apply the Fourier transform, easy and smooth, and so on. Since Alexander Leonidovich Skubachevsky has just say all important words about the consequences of the strong ellipticity, please let me mention this very briefly. So why do the Gordon type inequality, why is the Gordon type inequality important for us? It guarantees the well-known ninth properties of the Dirichlet problem. To list them, just we construct this sesquilinear form, and we know that it defines uniquely an M-sectorial operator by this formula with this domain lying in H10, and by the solution of the Dirichlet problem, we understand the solution to this equation, operator equation. And it is important to note once again that typically in the functional differential equations, this domain doesn't lie in H2 or even local. Here are the properties of the Dirichlet problem for the strongly elliptic functional differential equation. Unique solvability, continuous dependence on the scaling parameters in the case where they are incommensurable. The fact that the operator minus A is the generator of an analytic semigroup, and the Katic conjecture, and much has already been said about it. The proof for solvability is standard. The continuous dependence of a solution upon the scaling parameters follows from the uniform Gordon type inequality. And for third assertion, we employ the criterion from this monograph. And the last statement can be obtained on the basis of the classical result by Tosukat and Jacques William. Now the question arises to find algebraic criterion for the Gordic type inequality. Here this is the main slide for my talk. This algebraic inequality is necessary and sufficient for the strong ellipticity of the function differential equation. And it is interesting to look at the corollaries, quite obvious. Being strongly elliptic for fixed values of the scaling parameters p and q with incommensurable logarithms, the function differential equation remains strongly elliptic for all closed values as well. And it is strongly elliptic for all values from the range. Under this condition, the function differential equation is strongly elliptic for all p and q close to 1. And in the above cases, the Gordic type inequality holds uniformly with respect to the parameters p and q. And in the case of commensurable logarithms, this is no longer the case. For example, the criterion for the strong ellipticity of the function differential equation when q equals p squared is the following algebraic inequality, which is far away from the corresponding condition in the theorem, no matter how close q and p squared with incommensurable logarithms are. And here is another example of instability. If the coefficients are such that, then being strongly elliptic for p equals 1, the equation no longer possesses this property for all p greater than 1 arbitrarily close to 1. And I would like to finish my talk speaking a little about the case where the equation is not strongly elliptic. We consider a special case of the functional differential equation where we have this functional expression under the sign of the Laplacian. And in this case, the problem may be studied based on the properties of the function of this single functional operator. This lemma tells us how this operator act in the Sobolev space. Here we see that under these conditions. So what do these conditions mean? Q is larger contraction, and this inequality tells us that the larger contraction dominates in some sense. And and it turns out that this operator maps the space H10 of omega onto the space S10 of Q omega. Roughly speaking, since the larger contraction dominates, the support of the function expands. So you can see this is the difference, omega and Q omega. The support expands. This lemma yields the following statement. Of course, we impose some additional conditions on the domain, star-like domain. And the theorem says that under these conditions, the Dirichlet problem for this equation is solvable for all functions F, but the corresponding homogeneous problem has infinitely many linearly independent generalized solutions, non-smooth. The smoothness can be violated everywhere in the domain, and there are infinitely many such non-smooth generalized solutions. But what the most interesting for me is the following example. Please look at this carefully. We fix Q and we fix alpha. For simplicity, we take it positive. And alpha can be arbitrarily small. And then we consider this equation for p equals 1, and then for p greater than 1, and arbitrarily close to 1. And we see that the behavior is absolutely different. We have the jump, this jump in the behavior. The boundary for p equals 1, the boundary value problem is uniquely solvable, and every generalized solution is smooth. We can also prove this. While for p greater than 1, we have an infinite dimensional null space and non-smooth generalized solution. And all this happens for alpha arbitrarily small. From the viewpoint of the norm of these two terms, from the viewpoint of the norm, they can be neglected. But the case when p equals 1 and greater than 1, arbitrarily close to 1, have this dramatic difference. And summing up, I'd like to say that the situation is the following. The case where the scaling parameters are incommensurable is more stable in a certain sense. The things are more stable in the neighborhood of these incommensurable parameters. While for the commensurable parameters, the situation is unstable. So let me finish with this. Thank you very much.
Are there questions?
Thank you. I did not get if you am I right that if you have a strongly elliptic equation with incommensurable parameters, then all closed equations, maybe with commensurable parameters too, are also strongly elliptic. Yeah, yes. And dual question. You wrote the inequality and said in the very beginning, and said that it is this inequality holds due to the incommensurability of parameters, but the constant is just one. It does not depend. Yeah, that the norm of operator is greater or equal than the sum of coefficients, L2 norm. Yeah. Yeah. So the coefficient is 1. The constant in this inequality is 1. Does not depend on parameters. Yeah, but nevertheless, it is true only for incommensurable parameters.
Yeah, but I just cannot imagine how do the six relate to each other.
Okay. Okay, I don't know how do they relate in my mind.
Suppose P and Q are incommensurable.
Yeah.
Then we have the sum inequality necessarily sufficient for the Gordon type inequality. And it here it is. And we may slightly change P and Q. And,
no, this I understand. This was the first question I understand. But that question, the operator depends on commensurability of the parameters, but the inequality does not depend.
The first one?
Yeah.
Yeah, it does not depend. Yeah, it depends on the fact that they are incommensurable.
But the constant does not depend.
Doesn't.
Are there other questions?
It is interesting to know about your opinion for the following question. Just for one contraction, is it possible to generalize your results for a case of vector valued parameter p, for example? Just x is multi-dimensional.
Yeah.
And is it possible to consider p multi-dimensional too?
Yeah. This is what Ala Tasevich, who will speak later, is doing.
Any other questions? If not, let's thank the speaker. We will continue at 16:30. 7 minutes.
После каждого что делать? Вот это выключаю.
Раз, два, три. Отлично. Давай пока выключим. this is a one variable function. It depends only on y. Therefore, substituting it to equation 1, we obtain this ordinary differential equation on the positive half line. Hence, u0 of y is equal to py plus q, where p and q are somewhat are somewhat real constants. However, E0 satisfies problem 1, 2 in the Gelfand-Schilov sense. But this is a smooth function. Since it satisfies a problem, a boundary value problem in the distribution sense, it follows that it satisfies this problem in the classical sense. Then it satisfies the boundary value condition 2 in the classical sense. But in our case, the boundary value function is just the identical unity. Then E0 of 0 is equal to 1, but on the other hand, this is equal, let's set y is equal to 0 here, it is equal to q. So we obtain that q is equal to 0 here. Thank you very much, of course, to 1. Now, let's get back to the Repnikov-Edelman condition. This means that P is equal to 0. Agree? Now, we have excuse me, of course, this was plus Py, and now we know that since P is equal to 0, that this is equal to 1. Please look. It looks like something very well known, but remember that this is not a well-known fundamental solution of heat equation or of the Laplace equation. We know nothing about it. Well, not nothing, but we do not know its explicit representation. We know only this. And it turns out that for any collection of AK and HK, this integral is equal to 1. We even do not know that this function preserves its sign. And once we know this, we can use this representation and write. Now forget about our special boundary value function equal to 1 and consider arbitrary boundary value function u0. and obtain. Where kappa is somewhat a real point, depending on x, y. But anyway, this yields the maximum principle. Let me make a couple of notes, because probably this result looks a little bit more impressive than it deserves. First of all, in the classical theory of differential equations, the maximum principle is mainly used as an a priori estimate. So before we find a solution, we know that it never exceeds the somewhat constant, and it's lucky that this constant is the supremum of the solution at the boundary. Now we have it afterwards. But anyway, it's if you know about your function that it never exceeds its value, the supremum of its value at the boundary, you know a lot about it. Second, the second note, I never told you that the found solution is unique. And this is an open question yet. So at the moment, nothing is known about the uniqueness classes for this problem. But maybe this kind of derivation of the maximum principle can provide certain assistance, because, for example, if in this problem only constant boundary value functions are considered, then we have the following property. The problem has infinitely many solutions, but only one among them is bounded. And this is probably everything that I can say now. Thank you for your attention.
Are there any questions?
No, you see, it is, they are principally different. No, the answer is no. I see. Okay. This confirms the principal difference. I treat this as an additional confirmation of principal difference of problems.
Are there other questions?
Лень, дай ему микрофон. Да вот он микрофон.
Я тебе тоже что-нибудь скажу попозже, Андрей.
Ну, хорошо.
Andrei, could you please repeat why P equals 0?
Ага. Just a second.
Maybe it's already written on that.
I have wrote it somewhere. Just a second. Now, this is found, yes? And therefore it is equal to oh, sorry. Of course, Q is equal to 0 and P is equal to 1. Yes. No. Yes, sure. And on the other hand, C of x is reserved for this case where our initial, excuse me, not initial, there is no time here, where our boundary value function is just identical unity.
Thank you.
Are there other questions? I just asked one. I didn't, at the very end, you said quickly something about infinitely many solutions, but only one is bounded. Which were the solutions? I was completely lost at that point.
Each such function is a solution. Of course, I mean the case where our boundary value function is constant. Okay. In this case, it has infinitely many solutions, like this.
Okay.
But only one is bounded. This is the solution where P is equal to 0.
Well, if there are no other questions, let's thank the speaker again. And we'll break.
Ну что, я ухожу туда, да?
of arguments, please.
Так, Леонид Ефимович переведет.
I will translate.
В принципе, текст по-английски написан здесь.
Text is written in English here on the slide. So.
Я рассматриваю задачу 1.2. Это краевая задача для дифференциально-разностного оператора. При этом Q ограниченная область с кусочно-гладкой границей. И разностные операторы выглядят следующим образом. Здесь множество m1 и m2 – это конечное множество векторов с соизмеримыми координатами, причем перекрестно вектора из одного множества несоизмеримы с векторами из другого множества. Если в этой задаче убрать одно из множеств, скажем, m2 выбросить,
if we remove one of the sets in this problem, say m1,
это задача Скубачевского.
then this is the problem studied by
о которой он
Skobachevsky.
сегодня рассказывал, задача с соизмеримыми сдвигами.
Yes, then this is the problem with commensurable shapes that has already been discussed today.
Под решением мы понимаем решение в смысле выполнения интегрального тождества, это соболевское пространство.
Solution is the solution in the sense of this integral identity, an element from the Sobolev space.
Прежде всего будем исследовать условия выполнения неравенства 5, которое означает сильную эллиптичность. И это условие сильной эллиптичности известно как условие типа Гординга в теории функционально-дифференциальных уравнений.
Our goal is to study the inequality 5, known as the Gordon type inequality in the theory of functional differential equation.
Как Александр Леонидович уже рассказывал, выполнение этого условия позволяет включить данный оператор в класс операторов, которые удовлетворяют гипотезе Ката.
As was already told, these conditions allow us to include this operator into the class of operators for which the Kata square root conjecture holds true.
Как я уже говорила, теория краевых задач для эллиптических дифференциально-разностных уравнений с отклонениями аргументов в старших членах была построена в работах Скубачевского. Эти задачи имеют важные приложения в теории плазмы, в теории многослойных пластин и оболочек. Это я по-русски говорю. Но, однако, в отличие от задач с соизмеримыми сдвигами, здесь появляются определенные сложности. Во-первых, решение таких задач несоизмеримыми сдвигами могут иметь всюду плотное множество точек разрыва производных. Такой пример был построен Скобачевским для одномерного случая в его монографии. Сложности также связаны с определением условий сильной эллиптичности и условий положительной определенности соответствующих разностных операторов. И третье условие, это то, что даже малое возмущение сдвигов приводит к их несоизмеримости. И, следовательно, известные условия, необходимые условия, достаточные условия сильной эллиптичности, полученные Скобачевским, являются в этом смысле неустойчивыми по отношению к малым сдвигам. Я это обнаружила, когда только начала заниматься в студенческие годы этой наукой, страшно расстроилась, что решения неустойчивы. То есть, вообще говоря, мы, поставив себе такой вопрос, будет ли выполняться вот это, если вот это возмущение, это эпсилон, это не тау, эпсилон у меня, стремится к нулю, вот это вот возмущение в сдвиге, будет ли в норме пространства Соболева это решение возмущенное стремится вот к такому? Ответ нет. Ответ нет, сколь угодно малое возмущение портят все условия. Мало того, когда сдвиги делаются несоизмеримыми, вся эта конструкция вообще не строится.
And it was discovered by the author quite a long time ago that there is no continuous dependence of a solution on the shift parameters. Arbitrarily small perturbations of shifts may lead to this instability. So the solution of the perturbed problem doesn't converge to the solution of the unperturbed one.
Вот недавно, пару лет назад, Леонид Ильич Росовский как раз получил очень интересные результаты. Он начал исследовать непрерывную зависимость решений функционально-дифференциальных уравнений от параметра преобразования аргумента. И ввел или использовал такое понятие равномерной сильной эллиптичности, которое выполняется не только при фиксированных, замороженных значениях отклонений или сжатий или растяжения аргумента, но и в некоторой окрестности.
The notion of the uniform strong ellipticity was introduced recently in the paper indicated on the slide.
Ну и эта идея позволяет в нашей работе применять впоследствии, если уравнение является равномерно сильно эллиптическим, то мы можем осуществлять предельный переход. То есть мы можем возмущать сдвиги, и таким образом вот это равномерное условие сильной эллиптичности является устойчивым по отношению к малым возмущениям.
So the uniform character allows us to pass to the limit.
Ну, я еще раз выписываю разностные операторы, входящие в задачу. При этом сдвиги здесь из одного множества несоизмеримы со сдвигами из другого. Вводим операторы с индексом Q, которые учитывают размер области и форму области. То есть они продолжают функцию, по сути дела, нулем вне области Q. И далее мы строим разбиение области Q на непересекающиеся подобласти таким образом, чтобы сдвиги, входящие в оператор, либо переводили одну область в другую, либо выводили ее за рамки области. Это разбиение отличается от разбиения Скобачевского, которое он использовал. И у Скобачевского вместо множества m и минус m используется аддитивная Абелева группа, порожденная сдвигами. Очевидно, что при наличии несоизмеримых сдвигов построить аддитивную Абелеву группу и ее использовать невозможно. Ну, построить можно, но она будет бесполезной в данной ситуации.
The author uses a new decomposition of the domain into subdomains, different from that one exploited by Skobachevsky.
Ну вот и с этим разбиением лучше ассоциировать не группу, а граф. Под области это вершины графа, сдвиги это ребра. Если две области сдвигаются одна в другую, соединяем ребром и вешаем коэффициент из разностного оператора.
It is preferable and more convenient to use a graph instead of the Abelian group
И строим матрицы, которые являются, по сути дела, матрицами этого графа. Стандартным образом.
And construct certain matrices, which are the matrices of this graph.
И спектр разностного оператора, RQ, совпадает со спектром матрицы.
And the spectrum of the difference operator coincides with the spectrum of this matrix.
Теперь что мы делаем в случае несоизмеримых сдвигов? Берем первое множество сдвигов, они соизмеримы между собой. Строим разбиение, строим матрицы, находим минимальное собственное значение всех матриц и вводим оператор R с индексом C, проверочный оператор. То есть мы ко второму оператору из второго множества добавляем минимальное собственное значение, умноженное на тождественный оператор. И справедливо следует утверждение, что если этот проверочный оператор положительно определен, тогда и оператор RQ, состоящий из несоизмеримых сдвигов, тоже положительно определен.
The author introduces a special auxiliary operator and formulate the theorems in terms of the properties of this operator.
И рассмотрим простейший случай краевой задачи. Здесь R1, RQ операторы с несоизмеримыми сдвигами. И если оператор RQC положительно определен, тогда уравнение 6 является сильно эллиптическим, и краевая задача имеет единственное решение. И кроме того, вот такое мое, скажем так, разбиение позволяет в ряде случаев строить единое разбиение в области Q для несоизмеримых сдвигов. И в этом случае решение сохраняет гладкость в этих подобластях. То есть оно принадлежит локальному пространству H2 в этих подобластях. То есть разбиение может существовать.
And this new decomposition has some principal advantages. It allows us to select some cases where the smoothness of solution is preserved in the whole domain.
Вот пример 1, он же на досочке. Два оператора разностных. Тау – иррациональное число, меньше единицы, больше 2/3, ну, в этом диапазоне. Строится разбиение для первого оператора отдельно. Отдельно строим разбиение для первого оператора. По сути дела, вот оно.
The decomposition is only constructed for the first operator.
Если мы используем вот этот граф, то матрица этого графа, вот она на доске выписана. Минимальное собственное значение матрицы находим. Выписываем второе разбиение, ну я уж не нарисовал. Вторая матрица, минимальное собственное значение, вон оно, минус корень из 2, модуль А тау.
As for the second matrix, we need only the minimal eigenvalue.
Теперь переходим ко второму оператору R2, строим для него отдельное разбиение, оно существует.
And we do the same for the second operator.
Просто сила вот этих вот условий, это вот такое разбиение. И добавляем к нему, перекидываем от него мостик, перекидываем мостик от первого оператора ко второму с помощью просто минимального, вот это лямбда минимальная.
And this lambda minimal is the bridge from the first to the second operator.
Контрольный проверочный оператор, RC. Тогда положительная определенность оператора с несоизмеримыми сдвигами определяется им. И это простое условие 8, это положительная определенность матрицы этого оператора.
This condition 8 is the condition of positive definiteness of the matrix of this operator.
Это условие является равномерно сильно эллиптическим, равномерно относительно параметра тау, который меняется вот в этом диапазоне.
This condition is uniform with respect to the parameter tau, varying in this range.
Да, внизу написано условие сильной эллиптичности, основанное на символе разностного оператора. Нижняя строчка, видно, что она гораздо жестче.
Strong elliptic conditions in terms of the symbol of the differential difference operator, and it is much more restricted than 8.
При выполнении этого условия мы можем переходить к пределу, осуществлять предельный переход. Этой задачи, предельный переход, скажем, тау может стремиться к нулю.
Under the uniform ellipticity condition, we can pass to the limit as when tau tends to 1.
Предельная задача – это уравнение с соизмеримыми сдвигами. Легко строится соответствующая матрица, выписываются условия положительной определенности.
The limit problem is the problem with commensurable shifts, and it is easy to write down the matrix of the corresponding difference operator and calculate it.
И работа 3 – это работа Леонида Ефимовича Росовского. Можно, используя методы, изложенные в этой работе, показать, что в этом случае в норме пространства Соболева H0,1 решение будет стремиться к решению предельной задачи. А во втором примере я привожу как раз тот случай, когда возможно объединенное разбиение области. Этому разбиению соответствует вот такая большая матрица. То есть сдвиги, смотрите, тау здесь больше единицы, операторы примерно такие же. Но существует объединенное разбиение, и техника Скобачевского здесь применима. Разбиваем на области, строим матрицу и получаем условие положительной определенности оператора. Это условие положительной определенности матрицы R3 и матрицы R1. Но это условие является локальным, так же, как у Скобачевского. То есть оно не является равномерно относительно сдвига. То есть оно точное, но любые малые нарушения меняют всю эту конструкцию, меняют матрицу.
This condition is exact, but only for the commensurable shifts. Any arbitrarily small perturbations can change this situation completely.
Если мы используем раздельное такое разбиение, как в примере 1, мы получаем условия равномерной сильной эллиптичности.
But if we use the decomposition from similar to that one from first example, then we get this inequality.
Если оно выполнено, задача 6-7 имеет единственное решение для всех достаточно малых эпсилон, и мы можем переходить к пределу нормы пространства.
And if it holds, then we have unique solvability and continuous dependence of the solution.
Здесь мы имеем случай устойчивый. Ну, теперь я сформулирую условия для общей, более общей постановки задачи. Задача 1,2. Матрицы, вернее, разностные операторы его такого же вида, и получены достаточные условия сильной эллиптичности. Идея примерно та же. Перетаскивание. Строится раздельное разбиение для одних соизмеримых сдвигов, отдельно для других. И с помощью вот этого добавочка, здесь мы вычитаем, здесь мы прибавляем. Мы получаем достаточные условия сильной эллиптичности. Так, вот это мои статьи. Thank you for your attention. И вот это я в конце привела графики. Это одномерные случаи, аналогичные примеры. Вот это решение задачи с несоизмеримыми сдвигами в случае выполнения условий равномерной сильной эллиптичности.
So the simulation for the one-dimensional case, and the upper picture is, please repeat.
Это решение краевой задачи с несоизмеримыми сдвигами при условии выполнения условия равномерной сильной эллиптичности.
Under the condition of the uniform strong ellipticity.
Мы можем аппроксимировать иррациональный сдвиг последовательностью рациональных сдвигов.
We can approximate the irrational shift by the sequence of rational ones.
И полученные решения рациональных задач будут составлять фундаментальную последовательность.
And the obtained sequence of the rational problems form a fundamental sequence.
И она сходится к решению норме H1,
к решению
предельной иррациональной задачи. А слева это производная.
To the solution of the limit irrational problem.
А внизу та же задача, где условия равномерной сильной эллиптичности нарушены.
And below is the same problem, but when the uniform elliptic condition is violated.
Красное и черное – это решение задач при близких значениях отклонений, рациональных задач, но последовательность не фундаментальна. Даже малые нарушения приводят к резкому изменению, а это производная хаотичная.
Red and black zigzag lines correspond to very close values of shifts.
Такие задачи у меня студенты решают на спецкурсах по функциональному дифференциальному уравнению. Это лабораторные работы.
These problems are solved by the students of Елена Павловна on her course of functional differential equations.
Спасибо за внимание.
Let us thank Any questions or comments?
Я, может, по-русски спрошу.
Да.
Сходимость H1 рождается с тем, что граничные условия Дирихле как-то сносятся, да?
Нет. Отсутствие сходимости в H1, задача резко меняется. Если мы меняем чуть-чуть отклонение, меняется структура задачи.
Это я понял. А есть сходимость?
Вы знаете, в L2...
Потому что по этому рисунку понятно, что сходимости производных не будет, а вот в среднем квадратичном, может быть, и будет
нет,
сходимость.
здесь нету. То есть я проверяла. Если у нас критическое значение вот этого условия равно нулю, да, не больше нуля, а равно нулю, тогда есть сходимость в L2. Чисто эмпирически.
Ну, то есть я к чему спрашиваю? Значит, вопрос следующий. Во всех работах используется продолжение нулем, которое, ну, вот отражает тот факт, что, так сказать, задача Дирихле. В то же время в последних, во многих работах вычислительной физики для, например, в случае распространения лазерного сигнала уже не используется нулевое граничное условие, используется так называемые неотражающие граничные условия, которые позволяют избежать паразитных отражающих волн от границ. Может быть, использование вот этой вот техники неотражающих условий позволит избежать вот этой ситуации и какой-то новый всплеск вот этой деятельности.
Да. Мне кажется, что да. Спасибо.
Просто я, например, не видел, чтобы функциональные дифференциальные уравнения с неотражающими граничными условиями изучались. Вот. И там вот, может быть, вот такого вот эффекта не будет, а будет как раз непрерывность именно по преобразованию.
Спасибо. Мне кажется, что да. В принципе, да. Начало вопроса.
More questions? If not, let us thank the speaker again. She will speak about the solvability of functional differential equations with contractions in weighted spaces.
Thank you. Good afternoon, dear colleagues. My talk is devoted to elliptic function differential equations with contractions and their solvability in weighted spaces. First of all, I would like to define what type of equation I call elliptic functional differential equation. The general form of it is given by formula 1. Here alpha is a multi-index. D alpha is differential operator that equals this composition. The same is justified for beta. The operator R is a functional operator of arbitrary type. It could contain shift transformations, contraction transformations, or combination of these transformations. Thus, we consider 2m order partial differential equation in n-dimensional space with special transformations of variables of unknown function. I should also tell that to have really elliptic equation, one has to prove conditions of ellipticity. For functional differential equations, we generally use a Gording type inequality that is equivalent to the condition of strong ellipticity for partial differential equations. But this is not the topic of my talk today. So next, I would like to tell you a little bit about applications. The theory of functional differential equations began to develop in the 70s of the previous century. The interest was primarily associated with many important applications in non-local elliptic problems arising in the theory of plasma, in the theory of multi-layer plates and shells in aviation and astronautics, in nonlinear optics, in multidimensional diffusion processes, and in connection with Torsio-Kato square root problem, Torsio-Kato's conjecture about the square root of M accretive operators. Most of these applications are described by elliptic function differential equations, the principal part of which contains variable transformation that could map the boundary points inside the domain, for example, shift transformations. Alexander Leonidovich Skubachevsky made a significant contribution to the study of these applications and built a theory of elliptic differential difference equations. One of the principal properties of differential difference equations is the violation of the smoothness of solutions on a certain set of points formed by shift of the boundary inside the domain. The both boundary shifts divide the domain into subdomains, and the type of obtaining partition largely determines the properties of the equation. On this slide, I would like to show you three elementary but fundamentally different cases of transformations. As a domain, I consider a unit disk. In the first case, there is a shift transformation per unit along the first coordinate, and the disk is divided by boundary shifts into 4 subdomains. In the second case, there is a contraction transformation that acts the same way for each coordinate, or we call this type of contraction isotropic contraction. Here, under the impact of this transformation, an infinite number of concentric rings are formed. If the parameters of contraction are different for different variables, such transformation we call orthotropic contraction. Then the domain is also divided by an infinite number of subdomains, but the nature of partition is different. Let us consider the subdomains connected with each other by an equation containing both the function and the transformed function. On the first picture, there are two such domains, and the other two are not connected. Thus, the orbits of the points under the action of a group of shifts can consist of two elements or of one. In the second case, all the concentric rings are connected with each other. Hence, their orbits will contain an infinite number of elements, and they will be located on the rays going out the region. And in the third case, there are a finite number of connected subdomains, but this number grows unlimitedly when approaching excesses. This means that the orbit of any point, except the points of axis, contains a finite number of elements and is located on a hyperbola-like line. At the same time, the orbit of axis contains an infinite number of elements. Thus, this case can be said to combine the first two. I will speak about the third case. So let us consider the operator of orthotropic contraction more detailed. Fix parameters of contractions P and Q greater than unity, and consider a bounded operator P acting in the Lebesgue space L2 by the formula. Here it's inverse and adjoint operators. We obtain that the operator P is normal, and it's easy to prove that its spectrum coincides with the circle of this radius. Since we have already seen that the orbit of any point for the operator P lies on hyperbola-like line, we could choose the change of variable such that after it these lines transforms to the lines rho equals constant. And since the operator P acts along the orbits, it corresponds in new variables to the operator of contractions only by one variable. We consider solvability in weighted spaces introduced by Vladimir Alexandrovich Kondratiev in 1967 to study elliptic problems in domains with angular and conical boundary singularities. Since the solutions of differential difference equations have power singularities inside the domain, it turned out to be natural to consider these equations in weighted spaces also. These results were obtained by Alexander Leonidovich Skobachevsky in 1986. For functional differential equations with contractions, there is an additional singularity in the origin. And in the paper of Leonid Yefimovich Rasovsky, it was shown that we could always choose such parameter of weighted space that the equation is unique solvable. There is a unique solvability. Let us define the weighted space HS beta according to Kondratiev as the completion of finite smooth functions with respect to the norm 2. It was shown by Plamenevsky that the Fourier transform maps one weighted space to another with replaced parameters. And now let us state the problem. We consider on the plane functional differential equation 3. It is second order equation. Here the operator R, I, J are functional operators given by this formula. Coefficients are constant and complex. Parameters P and Q greater than unity. And function of the right hand side belongs to the space, to the weighted space HS0. Using the mentioned fact about the Fourier transform, we apply it to the equation and obtain the similar equation form. And also, since function vanishing in all quadrants except one form an invariant subspace of the operator P, we could go to the consideration of two equations. Here we can see plus, minus, and consider them in the first quadrant. Now let us make two changes of variables. First, I mentioned above, and the second is a logarithmic change that transform our contraction operator P to the shift operator T. And after all these changes, I would like to define the space where we work. I will denote it by Ks. It's a set of measurable functions for which the integral phi is finite. Here you can see a new weight. Let us introduce the following notations: alpha 0 plus minus 1 to reduce the length of our equations only for this, and we could formulate the intermediate result. We could consider not the inversibility, not the solvability of equation 3, but the unique solvability of equation 6 in the spaces Ks and its equivalent. Denote by E and by H these functions and these parameter, and let us rewrite equation 6 as follows. Here we can see the same weight that we saw in the space, in the norm of the space Ks. And this allows us to go to the Lebesgue space. So now we could go to the we could consider the inversibility of this operator B0 in Lebesgue space L2. Let us remark that the coefficients gamma of this operator have finite limits on infinity. This is we use sometime later, a little bit later. And the main condition that I need to get the inversibility is the difference from 0, one of the coefficients in the equation 6. I show you one. Equation 6. Here it is. So we want that the coefficients alpha minus 1 or alpha 1 differs from 0. If we set the function b0 like this, then this condition alpha minus 1 isn't equal 0 for any tau, can be rewrite as follows, as 8. And here we obtain the main result that if the condition 8 is fulfilled, and in addition we have these conditions fulfilled, then there exists the bounded inverse operator b0 minus 1. The proof consists of 2 steps. On the first step, we consider this equation only on a half-line I minus. The n is an arbitrary number, and we construct a solution. And we construct a solution and inverse operator with a norm that doesn't depend on n. And after this, we could continue our solution to the rest half-line I plus, and we get a solution on a whole line. So if we go to the initial notations, to initial problem, then they get this theorem 2. Here we can see that our conditions are depend on the parameter of the weight s, and changing s, we could change our conditions. For example, if we increase it, that gives us more weak conditions on one type of coefficients, and at the same time more strict conditions on the others. Here I would like to show you the publications where you can find the results about function differential equations with contractions, with orthotropic contractions. And I would also like to thank foundations for financial support. So thank you.
Are there any questions? So then let us thank the speaker again. And we have exactly 10 minutes break till the last talk today. Pleasure for me to introduce our next speaker, Claudio Gallegos from the University of Santiago, Chile. He will speak about measure functional differential equations with infinite time-dependent delay. So, please.
Thank you very much for the opportunity to speak here. This is a work in progress. Enjoy with Hernan Enriquez from Chile and Jacqueline Mesquita from Brazil. And well, the name of the talk is Measure Functional Differential Equations with Infinite Time-Dependent Delay. Measure functional differential equations with finite delay of this type have been introduced by Marcia Federson, Jacqueline Mesquita, and Antonin Slavik in 2012. This integral equation, y and f, are functions with values in Rn. The integral is the Henstock-Kurzweil-Stieltjes integral with respect to a non-digressing function g. Marcia, Federson, Mesquita, and Slavik established that functional dynamics equations on time scales represent a special case of this class of integral equations. And using the theory of generalized ordinary differential equations, they showed that theorems of existence and uniqueness of solutions, continuous dependence, and periodic averaging theorems. The equation 1 when the equation 1 is considered with infinite delay, was later studied by Antonin Slavik in 2013, and he worked on a phase space, finally similarly to the definition of the classical phase space in the theory of retarded functional differential equations, and he proved theorems about the existence and uniqueness of solutions. Well, we focus our attention on the equation 1, but with infinite time-dependent delay. That means we are concerned on the first argument on the function f of this form. It's a function. This form, where R is an appropriate function. And we will study this equation when the first argument is this form. Okay. Let me begin with the first definitions. The first definition is the Henstock-Kurzweil integral. If we consider a function delta, which positive values from AB, which we call it a gauge on the interval AB, and a tangent partition of the interval AB with subdivision points S0 is 1 to Sk, when S0 is equal A and Sk is equal B, and tags tau I belongs to the subinterval. The target partition is called delta fine if every subinterval is contained in the open ball with center in tau I and radius delta of tau I. Okay. Well, the definition, we consider a Banach space and a function u from AB squared to x is called Kurzweil integrable on the interval AB if there is an element I in x such that given epsilon positive, there is a gauge on the interval AB such that the norm of the difference is smaller than epsilon, and for every delta fine tangent partition of the interval AB. In this case, I is called Kurzweil is called the Kurzweil integral of the function u. And we will denote the integral by this symbol. Well, the Henstock-Kurzweil is still just integral of a function f from ab to x with respect to a function g, which appears in the equation 1 and the equation 2, correspond to the choice in the previous definition at the function u of this piecewise product. And we will denote the Henstock-Kurzweil Stieltjes integral by this symbol. Okay. Well-known theorems about the existence of the Henstock-Kurzweil Stieltjes integral is the following. If we consider a regulated function from ab to Rn, a regulated function is a function which in every point in the domain of the function, both the left and the right limit exist. Okay. But apart from the left limit of A and the right limit of B. So if you have a regulated function and a non-decreasing function g, then the Henstock-Kurzweil Stieltjes integral exists. And other theorem, if you have a function f and a regulated function g, and if you can ensure that the integral exists, then the function h defined by the integral, by the Henstock-Kurzweil Stieltjes integral from a to t, is a regulated function. Okay. Well, this is a definition. The definition is the prolongation property, and well, that we consider an interval of the real numbers, fixed point t0 in the interval, and Greek y is a set whose elements are functions from I to Rn. Then we say that this space has the prolongation property for t small greater or equal than t0 if for every function in the space for every function in the space and every t in this intersection, then the piecewise function y bar defined in this way is an element 2 of the space. Okay. You can think in the space, for example, in space of the continuous function, satisfies this property, and the space of all regulated functions from AB to Rn satisfies to this prolongation property. Another definition is the definition of the generalized ordinary differential equations. We consider a Banach space X, capital O, a subset of the Banach space, an interval, a compact interval of the real numbers, and a function, big F, from O, capital O times HP to X. Then a function, little x, from AB to O, is called a solution of the generalized ordinary differential equations on the interval AB if satisfies this integral equation where the integral here is the Kurzweil integral of the function f. Well, we can mention here that this is only annotation. Doesn't mean a derivative. Okay. Well, this definition or this class of integral equations was introduced by Jaroslav Kurzweil in 1957, and this class of integral equation have shown to be a useful tool in the to investigate other types of equations, such as impulsive retarded functional differential equations, functional dynamic equations on time scales. Volterra integral equations, among others. Okay. Well, our small contribution here in this work is that we can obtain a correspondence between generalized ordinary differential equations and measure functional differential equations with infinite time-dependent delay. Okay, it's the result. Well, in this context of infinite delay, we need work on a phase space. A phase space is the first argument, is the domain of the first argument of the function f, okay? The function little f on the equation. And we will employ the axiomatic approach utilized by Antonin Slavik in 2013. Okay? Then for us, a phase space will be a linear space H0, subset of the regulated functions from minus infinite 0 to Rn, equipped with a norm denoted by the symbol, and which satisfies four conditions. The first condition is that the phase space is complete. The second condition is that if you have a function in the phase space and a value is smaller than 0, then the history of the function belongs to the phase space. Okay. Another condition is that there is a locally bounded function k1 with positive values, such that if you have a function in the phase space and a value is smaller or equal than 0, then the value function y satisfies this inequality. Okay, when this is the norm on the phase space. And another property is that there exists a function k2 such that if you have a function in the phase space that the support is contained in a compact interval, then the function satisfies this inequality. Okay. Well, a clear example that we can use is the following example of phase space. We can think in the space of all bounded regulated functions from minus infinite 0 to Rn, endowed with the supremum norm. It's a Banach space, and furthermore satisfies the condition H1 to H4 with constant functions. Okay. Well, you can find more examples of phase spaces in the work of Slavik, and another work which appears other example of phase space which satisfies these conditions is a work of Giselle Monteiro and Slavik. Appears other examples. This is maybe the most typical example. Well, we also need a phase space of regulated functions defined on minus infinite a with a in R. But we consider this space like a shifting function from the phase space of the H0. Okay, and the norm is the norm given by the norm of the element of the phase space H0. Okay, and this space, this shifting phase space satisfies or inherit all conditions from the phase space H0. Well, we consider value t0, real number t0, sigma greater than 0, a subset of the shifting phase space H t0 plus sigma, subset P, which is a set of histories when x belongs to the capital O, and T is a value of this compact interval. we consider two function g, which is a non-decreasing function, and a function little f of this form. When the domain is the phase space H0. And for us, the function R, which appears here, will be a non-decreasing regulated function such that satisfies this inequality. Okay? And for each S in the domain of the function. Well, we consider two big F, this domain, capital O times integral to 0 plus sigma, to the space of all regulated functions from minus infinity to 0 plus sigma to Rn, given by this piecewise function. This function is a function that is 0 when G belongs to this interval, minus infinity to 0, is the integral, the Henstock-Court velocity integral in this interval, and is this constant when G belongs to this interval here. Okay. Well, we need to ensure that this function will be a regulated function. For that, we need to assume some conditions. The first condition is that this function is a regulated function, and therefore we can ensure that this function is regulated function. Another conditions following. There exists a function m with positive values, which is hence of course velocity disintegrable with respect to a non-decreasing with respect to the function g, which is a non-decreasing function, such that satisfies inequalities, bound inequality. And the last we assume this condition C, is that there exists a regulated function L of positive value, which is hence a integrable function with respect to the function g, such that satisfies this inequality. It's like a if-chit condition on the first argument of function F. Well, the results is this. If we assume the function big F is the function given by the equation 4, first equation, and take values in this shifting phase space, if we have a initial condition P, and capital O is a subset from the shifting phase space that that has the prolongation property for t greater or equal to 0, then if we have a solution of the measured functional differential equations with infinite time dependent delay, then we have a solution of a generalized ordinary differential equation of this form. And the other result under the same assumption is if we have a solution of the generalized ordinary differential equation on this interval with this initial condition, then we have a solution, an explicit solution of the measured functional differential equation. Okay. Well, this is the result that I will say. That is all. This is a reference of the work. That is all. Okay.
Any questions or comments?
Okay. Well, this idea of the function R was a question. This question, I don't know, was formed in the last year because we have a function y we asked why not consider a jump in the past. Not necessarily from all functions. Only the, I don't know how to say, it's like a loss of memory, where you don't know this part of the function.
Data up to time.
Well, in these two results don't have a really important these two results don't have an special let's say role, but maybe in other results that don't stay here. Yes.
More questions? Well, if not, let us thank the speaker again. Last talk, and we finish our afternoon session today. Thank you, everybody, for your contribution.